Hey, hello everyone. Today we are very happy to have Eslam Khalaf from Harvard University. He will talk about a bootstrap approach to the interacting Landau level problem.
Yeah, thank you. Today I'm going to start a recent work that I'm very excited about applying bootstrap a quantum many-body approach, like a numerical approach, to try to kind of as a new way to view the interacting Landau level problem. So this work is mainly based on so the talk will mainly be based on this work on the archive. Although I will discuss some stuff, or if I get to it, I may discuss some stuff that are a bit are not in this version, that would appear in a later version. And the work was mainly done by my postdoc, Chang Gao, but also with a lot of very important input from Ryan, who was a grad student with Lucas Witkowski at Washington, and now he moved to the perimeter. And also Patrick Ledwith and Jimmy, who was a postdoc at Harvard, and now he started a faculty position at Temple University. And I just want to start with some motivation, at least why I got interested in this problem. Of course, for many people in the audience, quantum home is an interesting enough problem that doesn't really need a motivation to look at it. But how I kind of got interested in the problem is that because in recent years I've been thinking a lot about these Moir systems, and these Moir systems really the one kind of, I'll give you the one slide summary why I think it's a very interesting system also from a theoretical point of view. So the main trick about Moir systems is it allows us to realize tunable isolated flat bands, which means we can really magnify the effects of correlation and get a lot of interesting physics when we project an interaction onto these flat bands. And of course, a very natural point of comparison to make is to see how these flat bands are similar or different from Landau levels. So Landau levels are kind of the most well-studied flat bands that we know of. And there's two main ways these systems differ or are richer compared to Landau levels. One of them is that they have these multiple flavor degrees of freedom. And at least for some of the flavor degrees of freedom, this is like a layered Landau level problem or spinful Landau level problem, where you're just repeating or like copying the same Landau level multiple times. But the really new qualitative ingredient you sometimes have in the system is that you can actually have two Landau levels that are effective Landau levels that are related by time reversal. So the whole system is time reversal symmetric. So you get kind of a lot of new possibilities there. And the second thing is that the Landau level wave functions have a particular and simple structure, while in these bands the wave functions can be a lot more complicated. And in particular, it means that the part density can be very non-uniform, and the very curvature that can be very non-uniform. And this is usually collectively referred to as quantum geometry. So you can ask what new physics one can realize in these interacting flat bands that are distinct from Landau levels. I mean, if we have Landau levels, why do we want to look for these kind of systems? And there's really two kinds of things. One of them is that you can realize a lot of phases in the same platform. So you can have the same system that has Wigner crystals, charge density waves, ferromagnets, superconductors, but at the same time also have some fractional topological phases, particularly just the possibility of having a superconductor and some abelian fractional topological phase in the same system is a very attractive possibility. Furthermore, we can also have these all these gapless phases, Fermi liquids, composite Fermi liquids. So it's really kind of maximally rich system in terms of the kind of phases that you can realize. There's also a lot of kind of interesting theoretical possibilities that you can think of this system that don't really have, you can think of as qualitatively new kind of phases. For example, you can look at time reversal invariant fractional topological phases, just because you have these conjugate Landau levels. There's also one very interesting possibility is that because in this system you break magnetic translation symmetry, so your anyons, are allowed to disperse. So anions in the Landau levels have flat dispersion, so the standard story is that they localize by disorder or they form a Bidman crystal, they form a crystal, but here they really can disperse, and there is a few recent proposals based on an old idea that you could get anion superconductivity. And another interesting story that, I will not get to talk about it today, but if you're interested, you can ask me about after the talk. I have some slides at the end if you're interested. But even you can get some interesting kind of mod physics in these bands. So these bands are topological like Landau levels, so you cannot get complete local mod physics. But there are certain limits where you get mod-like phases, but they still remember about the topology. So you can get something that we call a topological, a mod semi-metal in these kinds of bands. So this is, since most of my work in recent years have been about moir, I had to have a moir slide, but that's the only moir slide in my talk. So given this problem that builds off the Landau level problem, but has also a lot of extra new ingredients, we kind of want to ask, how can we make progress about understanding all of this? And in particular, if we want to understand like a bit more of the microscopics. So if we want to think of the kind of numerical approaches you can apply to this problem, then a very popular method for quantum Hall, and that has also been very popular in this field, is exact diagonalization. Of course, we know exact diagonalization can only be done for very small systems. You may get away with this when you have just something like a Laughlin state, which has a very short correlation length. But if you have competition between Laughlin state and other states, and if you also have these short distance momentum scale quantum geometry features that could actually give you other length scales in the problem, then exact diagonalization really shouldn't be something you can, that is reliable in any way. Of course, because these systems have a lot of symmetry broken states, also you can do Hartree Fock, but a lot of the things are completely invisible there. Also, the fact that these are not really described by lattice models. You're really the setup of the problem is that you have a flat band that is defined by some wave functions that are actually continuum wave functions, and you project your interaction onto this flat band. And in most cases, this flat band has a non-trivial topology, which means you cannot really write a basis of exponentially localized orbitals. So if you want to write a lattice model, it will have to be a lattice model that has power law decaying interactions and power law decaying hoppings. So many of the methods that people think about in the context of conventional strongly correlated systems like Hubbard model would not be applicable here. Quantum Monte Carlo, you can apply it. It's a fermionic problem, so quantum Monte Carlo can only apply it in a few fine-tuned points in the parameter space where there's no sign problem. So the more serious kind of approach is DMRG or tensor network-based methods. But these are 2D systems, so what you do is that you have to put your system on a cylinder and do some finite size scaling in the cylinder size, and it's ultimately exponential. And also in tensor network methods, you have a bias for gap law and entanglement states. So getting the competing gapless phases could be harder. All of this is saying that it's always good to have new methods, and even if no method is perfect, like some other methods could have complementary strength to these, and even if they have some biases, these biases could be different, so that can so we can get a kind of a complementary kind of information from the different approaches. So I want to introduce this method that it's kind of had a long history, but it's feels like only in recent years there is a growing interest in it. And I'll first explain it with a kind of a very simple example of basically trying to solve the Schrödinger equation without ever constructing the wave function. So let's say I have a very simple Hamiltonian, like p squared over tau m with some potential, some, let's say, polynomial in X. And the way you want to answer any question about this is to say, okay, I can find the spectrum, find the wave functions, and then ask about what is the value of some correlation function, like expectation value of x squared or x power 4 or some other observable in a given eigenstate, or even you can ask it about thermal state or other kind of state. But in the bootstrap approach, you really you want to completely sidestep the wave function. And although for this kind of problem, it may be just an unnecessary complication, when you go to the many-body case where the wave function is kind of lives in an exponentially large space, being able to sidestep the wave function and only deal with some correlation functions that live in a more manageable space would be a huge advantage. But yeah, if you want to think of bootstrapping this problem, what you would do is you look at different expectation values like x squared, x to the 4, generally x to the n, p to the l. There's also an important correlation function, which is the expectation value of the Hamiltonian, which is can be written, I mean, if this is a polynomial, it can be written in terms of these correlation functions. And then you impose a certain class of constraints on these correlation functions. The first one is just you have some operator identities. So if an identity holds on the level of operators, it also holds on the level of correlation function. So you would impose these identities. And this in particular will allow you to simplify this, to get rid of some of these correlation functions. The other class of constraints come from they come from positivity constraints, which means that if you have an operator that is a linear superposition or consider a linear combination of operators, then you form O dagger O, then you not only get the constraint that some expectation value is positive, but you really get a matrix of expectation values that should be positive semi-definite. And actually, positive semi-definite constraints are much stronger than regular positive linear inequality constraints. For example, usually when you look at the curve that this object gives you in parameter space, it would be nonlinear. It would be some convex region, but it's nonlinear, while regular equality constraints just can give you only a line. The last kind of constraints, so notice that all of these do not really select for expectation values in any state. So these are any expectation values that would be derived from any valid wave function. But if you want to select for expectation values that are evaluated in certain in eigenstates of the Hamiltonian, then there's these kinds of constraints. One of them is that if you, this one is stronger than this one. So this one tells you that if this is an eigenstate, an energy eigenstate E, and you take the expectation value of the Hamiltonian times any operator O, this is the same as taking E out and just taking the expectation value of O. And the first one just follows from the second one. So those acting with H from the left or the right gives you the same expression. And actually, in this particular case, if you take like a simple V of X, these kinds of constraints can be very powerful. It allows you to relate many of these observables to each other, so you can actually simplify these positivity constraints by relating these different matrix elements to each other. Anyway, I mean, I will not go through this kind of algebra in detail, but when you do this for a specific K, you can then you can just sweep over these variables, these expectation values like x squared and E, for example, and look for allowed regions. You can look for regions in the parameter space of x squared, of expectation value of x squared and E, where all of these constraints are satisfied. And when you do this, you get something like this. So notice that these two are looking for kind of different islands. So what you get broadly is that you get islands. So here is x squared, and here is E, and you get some islands that look like this. And this is a zoom in for the first island, the island close to the ground state energy, to the lowest energy state. And this is a zoom in for the second island. And you see that as you include more and more operators here in this K, this kind of island becomes tighter and tighter. So this K you can think of as your convergence parameter. And then the island tells you that there is an energy eigenstate around this energy, which in this case, I think they use the quartic potential with G equals 1, with prefactor 1. This is the ground state, and then this ground state would have a x squared expectation value that's around this value. And this is the first excited state. And yeah, you can see, for example, that the kind of the number of the convergence parameter you need to get different states, like ground state versus excited state, differs. So generally, for excited states, you need more variables.
Sorry, can you say in more detail, what was the input into this plot? Did you put in what was put into that plot?
Yeah, so so you think of x squared as some variable. Let's call it, you call it y1 and e as another variable y2. And you say, you sweep through the values of y1 and y2, and you ask, is there a choice of these expectation values that are consistent with this value of y1 and y2 and satisfies all these constraints? And when it satisfies this constraint, it's like the.
But you're agnostic as to the Hamiltonian?
No. So these two constraints know about the Hamiltonian. So this is where the Hamiltonian information goes in. So these two constraints.
It's a bit different than the usual bootstrap philosophy where you try to learn about theory space through the.
Yeah, this is the difference.
So what are you trying to learn about?
I'm trying to learn the spectrum of the Hamiltonian. I'm trying to, or the expectation, the spectrum of the Hamiltonian, or the value of some expectation values in eigenstates of the Hamiltonian. So this is not learning about the space of theories. This is a quantum mechanical bootstrap. It has a bootstrap philosophy in the sense that you use the constraints to limit the possible values of expectation values, but you're not really searching the space of Hamiltonians. You're just getting Hamiltonian to start with, and you want to learn about the properties of this Hamiltonian.
But then you fix a specific potential?
Yeah. So this is here it's a fixed potential, yes.
But do you know there's a state in your island? How do you know there's a state? Island.
How do I know there is a state? Well, I mean, if the procedure converges and like it keeps, I don't know there is a state because I can just, there is an x squared and an e where all the constraints are satisfied. Of course, that's what this method tells you. It tells you that there is a value of x squared and e that's compatible with all the constraints you can impose on the system.
No, but wait, but then you add more constraints and you realize some of that region disappeared.
Yeah, but the region will not shrink. Okay, it will shrink to a point, but there will always be a point. There will be always two bounds of the.
You probably need a separate argument to argue that the point does not eventually itself disappear. There is, I mean, if you increase without bound, the island doesn't just disappear. Probably.
Yeah, I think for any finite.
You can make such an argument.
Yeah, for any finite level. So can you answer this question? Like for any finite level of constraints, you'll have a region, but.
It requires completely different arguments. Like bootstrap alone does not guarantee you the existence, unfortunately. Yeah. Whether you have to show that the visible region is actually non-empty. And that's just another exercise that one has to do.
Yeah, but here also you have islands. So I mean, even if you show that the whole feasible region is non-empty, you then don't have a guarantee that some of these islands will not disappear at a certain level. I mean, that's not exactly what we will be doing because we'll be looking at the full feasible region of states. So we know that this region is not empty. So we know that this will not shrink to a point. So that's not exactly what I will be doing. It's just a motivating example.
Is there an easy way of seeing why they're disconnected at all? Is there an easy way of seeing why they're disconnected?
He's getting the whole spectrum.
Yeah.
I know, but why do they actually disconnect? I mean, there's some
Well, the
effective
spectrum
gap.
is discrete, so hopefully.
Yeah, so if the spectrum is discrete and you put
Enough
all the
constraints.
constraints you can put, you should reproduce the spectrum. So you should expect at some point that the islands start disconnecting. Yeah, I mean, if they don't disconnect, then you haven't imposed enough constraints. But at least, I mean, this is an illustration that you can have examples where they disconnect, and they disconnect around the points where you get these where the actual spectrum. I mean, this is a problem. That's a very easy problem. So we know what the spectrum is and what our properties are. the case I would be considering would be looking at the many body space and just trying to upper and lower bound stuff. So I have, there it's enough, there are the constraints I would impose are just restricting me to a space of physical states or physical density matrices. And there I know that at least one physical density matrix exists. So, but also here, I mean, I know that at least one wave function, one valid wave function exists that would give me some x squared and some e. So at least I know that not all of these regions can shrink to, can disappear. I mean, it's a good question whether whether there is any guarantees about the stability of individual islands. I don't know if you can make statements like this here. Yeah, so the idea of this so-called quantum many-body bootstrap is to use this this idea, or it's kind of a related set of ideas, to solve a many-body problem. And to solve a many-body problem, I mean, we want to make statements about, for example, the ground states of certain Hamiltonian or the excitation spectrum, or in all of cases, we can actually make rigorous lower and upper bounds about correlation functions of this Hamiltonian in the ground state, or now there's even extensions at finite temperature. So the basic idea is the following. So let's take a density matrix rho. So naturally, a density matrix rho defines a linear functional on the space of operators that just obtained by taking the expectation value of the operator in the state defined by rho. And this linear function now satisfies certain properties. The most important one of them is positivity. So for any positive semi-definite operator, which in the polar space we can write as OO dagger, this expectation value is positive semi-definite. And we can also make the opposite statement, which is that given a linear function, that satisfies this positivity condition, we can find a physical density matrix such that the linear function is given basically by tracing over this density matrix. The idea of bootstrap is to relax this condition to imposing the positivity only to a subset of operators. And once we relax this condition, we are now searching over the space of linear functionals that don't necessarily correspond to physical density matrices, but could correspond to density matrices that are not positive, but could have some negative eigenvalues. But what is guaranteed is that the set of linear functionals we are looking at includes all possible linear functionals defined on physical density matrices, which means we're basically searching a superset of the possible physical expectation values. Then it follows that if we minimize or maximize any quantity over the set, so if we minimize the quantity over the set, we get a lower bound of that quantity over the space of physical density matrices. So we think that this is the space of physical correlation functions, or defined by a physical density matrix, and we are looking at correlation functions that satisfy a subset of the physicality conditions, which means we are considering a superset. And we are minimizing some physical quantity, let's say the Hamiltonian, over the set. And if we minimize the Hamiltonian, we are guaranteed that the energy minimum we will get would be a rigorous lower bound to the actual energy minimum. We can also do it by upper bounding, by maximizing the quantity to get an upper bound. And clearly, as you add more and more constraints, you are actually approaching the space of physical correlation functions. So this way of kind of introducing the bootstrap approach, of course, is is agnostic about what kind of states you are evaluating your correlation functions at. So, for example, if I want to minimize the Hamiltonian, of course, the Hamiltonian will be minimized by a state that's also an eigenstate, which means that I can impose a lot more constraints than just the constraints that are required by positivity, which basically select for any physical density matrix. Here, I'm also I should also restrict myself to density matrices that are that correspond to eigenstates, or actually to the ground state. And that's why in the bootstrap community, people have also, or quantum Hall bootstrap, people have also been imposing some other classes of constraints. So yeah, so some of these are called these equation of motion constraints, which is basically this is the same condition I wrote earlier. So this is the statement that the commutator of the Hamiltonian and any operator expectation value. So this is a statement that is true for any eigenstate of the Hamiltonian. It's also true for Gibbs states. So if we want to do, although we can do this kind of bootstrap idea, if we just want to minimize, to do something like minimizing the energy or minimizing the operator over the whole Hilbert space, we can just use the positivity constraints. If we know that there's some additional properties of the state we are aiming for. For example, if we're minimizing the Hamiltonian, we're asking questions about the ground state, or if we want to ask questions about about certain bounds of operators evaluated in the ground state, then we can impose these extra conditions that actually select density matrices that correspond to the ground state. So one of them is this equation of motion that, as I said, selects for eigenstates or Gibbs states. The other is this identity I wrote earlier, which is a stronger condition. So this selects for eigenstates of the Hamiltonian, energy eigenstates. And the third one is something that's usually being called perturbative positivity. So this is basically the statement that if this expectation value is evaluated in the ground state, there is no operator that acts on the ground state that can reduce its energy. So this condition is basically this condition, O dagger HO minus is larger than or equal H O dagger O. But this is, well, I mean, if this is evaluated in the ground state, then this is the second inequality. So this is a statement that so the variational energy of any excitation has to be larger than the ground state if I'm evaluating this expectation value in the ground state.
Why do you call it perturbative positivity? What's perturbative about it?
I think I use the name from some other paper. So I think usually you'll have you cannot, I mean, if you include this for all operators, then it's not perturbative, but usually you would choose a few body operator or a very local operator. So this is a small perturbation on the ground state, not completely a different ground state. Yeah.
Can the first two conditions be written in terms of two product identities?
The first two conditions, you mean?
This one, yeah, and the product identity. Can you just replace the first one by another product identity where you switch H and O?
This product identity is stronger than this. So once you impose the product identity, I mean, you impose it from the right and from the left, then subtracting, you get the first one.
That's fine.
Yeah. So this one is weaker than this one. But sometimes you may impose this and not this.
But I guess you need two to replace the first one.
Yeah, so you need the one also from the Hamiltonian acts on the other side. Yeah. Yeah, I also just want to mention that this, although this is a very abstract and general approach, the applications of this method has been mostly focused on thin lattice models with local interactions. So it's not immediately obvious how this approach would work for something like the interacting Landau level, or even this interacting Chern bands, where we have fermions, they are projected, they are living in the continuum, they are projected onto some non-trivial Hilbert space. Of course, we know fundamentally that all of this, that this will should generically work, but in practice, we don't know how well these ideas would work for something similar like the Landau level problem. However, here I just included some incomplete list of references of where this idea have appeared, particularly in the condensed matter context, and some of these papers predated this idea of quantum or quantum many-body bootstrap. So they, of course, they didn't use the bootstrap language in this, but more recent work kind of tried to connect this to broader ideas that came from the bootstrap community. But it turns out that actually there was an approach that was known for a very long time in quantum chemistry that basically have most of the same elements of what we're doing here, which is basically trying to solve a quantum mechanical problem, which means trying to find correlation functions associated with the ground state of a certain Hamiltonian or some eigenstate of a certain Hamiltonian without ever really constructing the wave function explicitly. And these are, this is really something that was pioneered by David Mazziotti here at University of Chicago. And they usually have the name, maybe not a very descriptive name, called wave function free methods. So, so the idea of this whole field started by a very kind of interesting article by Coleman, where he posed the question, if I give you some matrix that is supposed to describe the it's a two-particle reduced density matrix of some fermionic system. How do I check that this derives from a valid n-fermion wave function? And this problem was termed the n-representability problem. People have already, in the early works, people have derived partial n-representability constraints, which means they have found necessary but not sufficient condition that would allow you to check if a given matrix that's like satisfies obvious stuff like positive semi-definite remission and antisymmetric is a reduced density matrix, is a valid reduced density matrix for a quantum system. And they've already used this idea to derive lower bounds in the ground state energy. So if you take the space under the set of constraints, which is necessarily bigger than the space of physical two-particle reduced density matrices, and minimize the energy, you would get a lower bound on the ground state energy. There's also some idea that appeared in this community called the contracted Schrödinger equation. And the contracted Schrödinger equation is very similar to this operator product identity. So it asks a question about if you take the expectation value of the Hamiltonian times a two-body operator, that's a four-body operator, and then you relate it to the Rydberg identity. So if you take this to be the 2-RDM, this would be an equation in terms of the 4-RDM. So there's an identity that relates the 2-RDM and the 4-RDM. So you can write some of these consistency conditions for the two-particle reduced density matrix. And there's also other consistency conditions that relate the two-particle reduced density matrix to the four-particle reduced density matrix, because two-particle reduced density matrix is obtained by tracing out some degrees of freedom of the four-particle reduced density matrix. So when you kind of combine these relations together, you can get tighter bounds on the ground state energy. But of course, the problem is the four-body reduced density matrix is kind of a very big object. So you need to do some certain truncations and certain approximation. But I'm just think it's interesting that this kind of idea has already was already discussed in this literature. Now, in terms of the kind of the theoretical progress about this problem, there was a paper in 2007 that proved that this n-representability problem is generally in QMA hard. It's not really a surprise. So given a candidate density matrix, you cannot really, it's a hard problem to tell if it's n-representable or not. This is kind of an instant or analog to the quantum marginal problem for fermions, for the case of fermions. And there was an interesting result by Mazziotti where he showed that, you have to check exponentially large number of constraints, but he showed how to construct kind of a complete set of those exponentially large number of constraints. So, and this construction provided, in a sense, a hierarchy of constraints that you can impose level by level. And although they're exponentially large, at least in practice, it seems that you can get good convergence when you impose only a few levels of this hierarchy. And I just want to also emphasize or mention that the problems quantum chemists are interested in are kind of the complete opposite to the problems that has been studied in these bootstrap works, because they work explicitly with fermions in the continuum with two-body interactions that are not necessarily local, because you're thinking of, for example, long-range Coulomb interaction. So just the fact that this kind of approach has been emerging from kind of two different directions is telling you that this seems to be a very kind of broad and versatile approach. And in particular, the quantum Hall case has a lot of similarities actually to the quantum chemistry problem, because we have fermions in the continuum with two-body interactions, and it can be long range. But there's also an extra structure, and the main thing I want to discuss is how do we exploit this extra structure to actually show that this method can give us quantitatively accurate results about interacting Landau level. So, just briefly, I mean, I'll go to the technical details, of course, about the quantum Hall or Landau level problem, but as I said, I motivated my talk by broader range of problems, but quantum Hall problem is really the prototype that you have to start. It's where you have to start if you want to develop any new approach that addresses this difficult problem of kind of interacting flat bands. As I said, there is some qualitative aspects of this problem that makes it a bit harder than, or a bit more complicated to apply many conventional methods, because we're thinking of electrons in a continuum. We have a long-range interaction, so we don't really have straight locality, and we don't have a lattice representation. The problem can be studied on several geometries, and each geometry has its own advantage. So it can, different geometries have different symmetries manifest. Of course, in the thermodynamic limit, the results we get in any geometry should be the same. There's also a very kind of rich analytic structure that I will discuss later, and that in most methods is actually not exploited. So a new method that can exploit that analytical structure can actually allow us to make progress, like a quantitative progress in understanding the problem. There is of course, some general field theoretic or broad universal physics we can make about this system, but also there is a few analytically controlled limits, like these pseudo-potential limits. But a lot of questions still can only be answered numerically, like through ED or DMRG. And yeah, it's have already a rich phase diagram, so we can already look at many different phases and competition between them and so on. So let me just discuss the very basic setup. So so I will think of a density-density interaction projected onto a Landau level. I mean, for most of the talk, I'll just discuss the lowest Landau level, but this setup can work for any Landau level. You'll see later that that's actually the most general interaction you can write once you project due to a certain symmetry of the Landau level. And these density operators these are the projected density operators, not the microscopic density operators. And they are obtained by taking, so the microscopic density operator at wave momentum q is represented in first quantization as e power minus iq dot r. And then you compute the matrix elements of that in a certain basis that parameterizes the Landau level. And this basis depends on the geometry you take. For example, on the sphere, you take a basis that's a representation of rotations on the sphere. On the disk, you take an angular momentum basis. I'll work on the torus, so this would be a momentum basis. And I will discuss in detail what basis I will be using. A very convenient way to understand this projected density operators is to define something called a guiding center coordinate. So it turns out that the coordinate, the spatial coordinate R, splits into two pieces. One of them is the dynamical momentum, and the other is this guiding center coordinate. And in terms of these, the projection to the Landau level, on a Landau level is very simple. You just throw away this dynamical momentum part. So what you get is just replacing R by this guiding center coordinate. And the main complication you get when you do this is that these guiding center coordinates no longer commute. So they are the x component and the y component are canonical variables to each other, and this is kind of responsible for all the richness of this system. For example, it has UVIR mixing because momentum in x is position in y, and you have a lot of kind of interesting structure. So if you want to write things in terms of this guiding center coordinate, the main difference is that you have to extract this Gaussian factor. So you can write the interaction in terms of this modified density operator that describes actually the guiding center coordinates rather than the microscopic density operator. And the full interaction has this extra factor. This extra factor, interestingly, tells you that effectively the interaction becomes short range because you get this Gaussian in the momentum space, which also gives you a Gaussian in real space. For the remainder of my talk, well, first I'm assuming something, which is that all of these, of course, this has units of length, this has units of length, so here should be units of length squared. So all the expressions here should have some LBs, the magnetic length contained, but I will set from the very beginning my magnetic length to 1. So one thing. The second thing is that for the remainder of this talk, I will drop this GC. I'll drop this guiding center coordinate. So all the densities that we're talking about will be the guiding center density operator. This is also the standard. Yeah.
Oh, sorry, just to make sure I understand. So in your row GC, your like original C dagger and C.
Yeah, actually, so I think, okay, this was not a good way to present things because here I'm writing things in first quantization while here I'm presenting things in second quantization. So you should think of rho GT as written in the same way, but these lambdas now have here capital R instead of small r.
I see.
Yeah, so yeah, this wasn't modified the slides, I forgot to modify this, but yeah.
You say that the interaction becomes short range?
Well, it becomes not short range. It has a Gaussian. In the case of there's a Gaussian factor, Gaussian decay factor from this.
If it's long range, then it's still long range.
Well, yeah,
if it's Coulomb, then it's still.
It's still Coulomb, like in that the interaction microscopically is long range, and there are certain aspects of the physics that depend on this. I'm just meant that all the expressions that involve this do not really. There are no issues with using a long range interaction because this kind of guarantees the convergence of any expression. But yeah, I don't. So that when you project, okay, let me try to make this more precise. So of course the interaction is long ranged. If you have two projected density operators and you express them in terms of this natural coordinates in the lowest Landau level, the effective well, this Gaussian factor will give you an effective decay as a function of R minus R prime.
Short R, not long R corresponds to small q. It doesn't q.
Yeah. See it? Yeah. Yeah, this cuts off short distances. Yes. So if you have a delta function, then it doesn't become contact interaction. It becomes it's smeared over LB distance. You're right. Okay, and just there's a simple modification of this interaction that if you go to a higher Landau level, so it just when you go from the density to the guiding center coordinates are exactly the same, but this effective Gaussian factor is replaced by something that has a Laguerre polynomial, And so this is the main difference between the lowest Landau level and higher Landau levels. And I'll work explicitly on the torus. So I'll consider n particles on the torus and n5 flux quanta, so that my filling is n over n5. So my filling mu is n over n5. Now, an important property of the of any Landau level is something called continuous magnetic translation symmetry. So because the Hamiltonian only depends on the guiding center coordinates, I can define the operator. I'll define it this way, where here R is the guiding center, and this wedge is defined this way. So this operator acting on a function. Oh well, here I'm making some gauge choices. But this operator acting on a function, it does two things. It shifts the spatial coordinate by u, but it also does multiplies it by some phase factor that's R dependent. So does some gauge transformation. And the really kind of gauge independent aspect of this operator is its commutation relations. So these operators satisfy the magnetic algebra, which means TU and TV, instead of commuting, they commute up to this phase. And you can think of this phase pictorially as the flux enclosed in the parallelogram formed by U and V. What this tells us is that if we choose a unit cell that contains 2 pi flux, which means that we take A1 and A2 such that the cross product of A1 and A2 is 2 pi, and form a lattice with these, then the translation, these magnetic translations corresponding to these lattice operators all commute with each other. And the fact that these commute with each other, of course, also they commute with a non-interacting Hamiltonian, which is in the R basis just 0. So we can choose a basis of the Landau level that are eigenstates of these. And so these would be Bloch states, analog Bloch states. They have an explicit expression in terms of Jacobi zeta functions or sigma functions, but I will not write it here. And this minus sign here is a convention. It makes everything a lot simpler. But the main idea is that these are just Bloch states. So this is psi k of R, and this translation acts on the R index, and then it gives me this phase factor. They look exactly like Bloch states. Now, so I can now express any operator in the lowest Landau level in terms of creation relation operators of electrons labeled by this momentum, this Bloch momentum K. And I have an action of this magnetic translation in second quantization, this momentum basis. So it turns out that this magnetic translation acting in this momentum basis, what it does is it shifts K by the vector that's orthogonal to U. This is related to some duality between real and momentum space in Landau levels, but also multiplies by this extra phase. And now let's say I want to look. So my system, now I have a Hamiltonian that has magnetic translation symmetry, has this symmetry, and I want to insist that I'm looking for that my ground state, the ground state density matrix will have this property, will have this symmetry. Now. Okay, no, sorry. That's what I will say later. So just before going through this in detail, we can just notice immediately that if we look at fermion bilinears and insist a fermion bilinear satisfies is invariant under this operation, then the only fermion bilinear that's invariant under magnetic translation for all U's is just the density at Q equals 0, which is just a total particle number. If we look at 4 fermion operators, which I mean, there's many of them, but we'll find that if we impose this condition, which means we look at fermion operators that are invariant under this magnetic translation, find that they are only this combination, rho Q minus Q. This tells me that the Hamiltonian I wrote earlier is actually the most general Hamiltonian consistent with continuous magnetic translation. There's no other terms you can write. So yeah, the main simplification we will do when we're looking for, when we're doing this bootstrap and we're looking for these expectation values relative to our density matrix is to assume that our density matrix is invariant under magnetic translations. This is not a restrictive assumption because even if the state breaks this magnetic translation symmetry, like it's a charge density wave, we're looking at density matrices. So we can always take the density matrix that is averaged over all symmetry sectors. So this simplification doesn't really miss any of the physics we are interested in looking at. But this means that the only non-trivial operator up to 4 kind of Fermi creation operators or up to 2-body operators is this operator, is a density-density correlation known as a static structure factor. And in general, magnetic translation will reduce the number of variables for a p fermion correlation function from something that scales as n phi to the 2p to n phi to the 2p minus 1. So it gives us an n phi squared simplification, n phi squared speed up. So now I'll just discuss what is now the setup of the problem. So what we want to do, so the first question I want to answer is whether I can use this method first to estimate the ground state energy as a function of, or to bound the ground state energy as a function of some parameters, and whether the correlation function associated with this minimization describes the correct correlation functions evaluated in certain quantum states, for example, a Laughlin state or a composite Fermi lakelet. And as I said, all 2-body correlation functions are encoded in this guiding center structure factor, which means I can really do this full 2RDM using this variable SQ. And that's a very convenient variable because if I look at the number of variables that characterize the 2RDM, they go as n phi to the 4. But the number of variables that characterize the structure factor is n phi squared. And the way you can see this is that rho q is just a linear superposition of C dagger alpha Z beta. Each of alpha and beta go over n phi squared. So there can be at most n phi squared independent rho q's, linearly independent rho q's. And it turns out that actually this matrix is invertible in terms of in Q and alpha beta. So the number of independent rho q's is indeed n phi squared, if you do not know whether these are fermions or bosons. But we know that these are fermions, so there has to be one extra constraint imposed on this SQ. So this SQ, which is a density, we don't know what object these densities are formed from. We don't know whether these densities are densities of bosons or fermions. So there has to be one extra condition. So here you have this n phi minus 1 over 2, and here you have n phi squared. And whether there's actually a further simplification that reduces the number of variables that tells us that this is a density correlation that's built out of fermions. And it turns out there is, so this is related to a duality or a set of sum rules that was derived by Haldane. So I'll go through the derivation quickly because it's maybe not the main point, and also I'm running out of time. But the main duality has this form like this. So you define just this small SQ, which is the capital structure factor with something subtracted. And then you see that it's a self-dual under Fourier transform, where the plus sign you get for bosons, if you do quantum for bosons, you get the plus sign, and the minus sign you get for fermions. And you can think of this as that this SQ satisfies an infinite number of sum rules for every momentum. This actually reduces the number of independent variables from n phi squared to n phi minus 1 over 2. So we can use the structure to significantly reduce the number of variables that we need to kind of to describe this. And there's kind of an easier way to derive this Haldane duality, which is just to write C dagger C, and notice that there's kind of 2 different ways to combine or contract these C's and C daggers into densities. One of them is to just do the 2 that are next to each other, and one of them is to take the last one and combine it with the first. And the 2 differ by first a minus sign from fermionic relation, fermionic anti-commutation, and some other terms. If you use the form factors of the Landau level, you get the Haldane duality. So I like this derivation because it tells you that actually this could hold for more general systems. So you can generalize this identity beyond the Landau levels, beyond the lowest Landau level. So the second thing is the positive semi-definite constraints, which I discussed earlier. And For the setup we want to think about, we want to really, since we have this huge simplification where we express everything in terms of the structure factor SQ, we want to write the most general positivity constraints that can be expressed as a constraint on the structure factor SQ. And there's of course one obvious choice, which is to take O dagger O, where O is a fermion bilinear. So because if O is any fermion bilinear, we can rewrite this object as some positive semi-definite constraint on SQ. And for example, we can take, if we take this bilinear C dagger C, we will find that you get a matrix that depends on SQ that should be positive semi-definite, but you notice that this matrix is actually related by a unitary transformation just to SQ. So this constraint is in a sense trivial. It just reduces to the linear constraint that SQ is larger than or equal to 0. We could have just imposed this from the beginning. But if you instead do the CC, you do get actually a non-trivial constraint. It's a positive semi-definite constraint. So you get a matrix that is constructed out of SQ, depends linearly on SQ, constructed out of SQ that needs to be positive semi-definite. And if you do C dagger, you get a constraint that's stronger at filling larger than a half and weaker at filling less than half. So if you just do the half and use particle symmetry, you don't need the other constraint. But then there's actually more constraints that we can impose by using this Maziotti hierarchy that was discussed in this quantum chemistry literature. And this may be one of the kind of the main non-trivial thing about this hierarchy, which is that you can actually impose constraints on low body operators like the structure factor or the two-body density matrix using high body operators. And the simplest way to see this is to consider, for example, a three-body operator like this, or you can take CCC. Now, if you just look at O dagger O, yeah, it's positive semi-definite, but this will not be expressible in terms of the two particle reduced density matrix, 2RDM. But if you take the combination of O dagger O and O dagger, you find that due to fermionic anti-commutation, the 6-body piece or the 3-body piece cancels out. So this still gives you a constraint that is completely expressible in terms of 2RDM or in terms of the static structure factor SQ. And commonly used 3-body constraints in quantum chemistry, they are called T1, which is obtained by taking CCC, and T2, or generalized T2, which is obtained by taking the most general C dagger plus C. And this is actually, so Maziotti has constructed this full hierarchy where he said that the full solution to the n-representability is to take all sets of p-body operators and look for combinations of them of this form, like OI dagger, such that all the p-body terms cancel and you're only left with 2-body and 1-body terms. It's not a very kind of, I mean, Maziotti gives kind of a way or the way to construct this, but he has a general proof that if you impose all of these constraints, then you ensure that your 2RDM is a physical one. Of course, the problem is most of these constraints are not really positive semi-definite. So if you write a general form of an O that has some AIJK, CI, CJ, CK, and you try to look for combinations where these terms cancel, you'll see that you need to impose a condition of tensor factorization on A, which actually means that the constraints you get are not positive semi-definite. You require a matrix to be positive semi-definite when acting on a certain tensor space. So they're not very useful for kind of numerical implementation. So we'll stick to these kinds of constraints. I also want to mention that you can also look at these equation of motion constraints. These are because of magnetic translation, there's no non-trivial fermion bilinears. So the simplest operator you can write for the quantum hole is a density. But then you'll see that this equation will be an equation that requires 3RDM. So you cannot write a 2RDM equation using this. Similarly, the product identity would actually need a 4RDM. These stability constraints, you can use them to write constraints on the static structure factor and SQ. But what we have found is that these new constraints do not really give tighter lower bounds. They can give us upper bounds, but these upper bounds are much worse than you get from variational estimates. So I mostly stick to the other constraints, but I'm just saying that we consider these, they just, in the simplest setup, they don't help us that much. And this is just a very brief statement about what I'm doing. So I'm considering a screen Coulomb interaction. I will subtract this, when I write the interaction in terms of density, but of course, when you the actual first quantized Hamiltonian is a normal ordered one. So when you do this normal ordering, you subtract off a piece. So, and sometimes I would want to expand the interaction in terms of so-called pseudopotentials. I'll explain later, like when we get to this, what do we do with this? But the main point I want to say is that when we take the limit of screen Coulomb interactions, short screening distance, we approach the pseudopotential limit. And the pseudopotential limit, for example, the Laughlin states are known to be the exact ground state. So the first thing we can check is whether this approach does what it is expected to do, which is give us lower bounds on the energy. And here we can just compare with ED on small systems, because this is just to check that we're doing everything right. And yeah, so the two things we see is that we do get a lower bound on the energy. Here I'm changing the screening distance. But the other important thing is that, yeah, this lower bound gets tighter as we go, for example, from this two-body constraints to the three-body constraints. Numerically, the energy error measured in the right units is around 1%, which actually is comparable to, or even smaller than the errors you would get from finite size scaling when you consider the system on a very small system size like 3.5. So at least compared to ET, the systematic error you get from here could still give you more accurate estimates for energetics, for example, compared to ED. There's one interesting thing if we look at the error as a function of the number of particles. We do see that there is a very big spike as we at this particular filling, as we go from 8 electrons to 9 electrons. This is on 25 by 25. And there's another smaller spike at this filling as we go from 5 to 6. These are not random points. These are precisely the Laughlin fractions. And it's telling us that somehow when we add electrons to Laughlin, that this method underestimates the energy. And I'll get to this point later. But the main information, of course, we want to extract from this is not just information about the energy, but we want to see if the correlation functions that minimize the energy actually give us, they look like the correlation function we expect. And one way to characterize, for example, for the 1/3 filling, which corresponds to the Laughlin state, is to look at these so-called pair correlation function. The pair correlation function is related in a simple way to this density or the static structure factor. And its main feature that tells us this is a Laughlin state is that it should behave as R to the 6 at small distances, because that's what tells you that when two particles approach each other, they have a higher order 0. And this is reproduced perfectly here. So the short distance, the physics associated with how the two particles approach each other in the Laughlin state is the structure factor that minimizes our state is reproduced perfectly here.
So these are the expectation values that are recovered from the solution of your bootstrap problem.
Yes. When I minimize, I just look at what solution does minimize things. There is an interesting case where if I use this, there's a certain potential where I can actually have a degeneracy, so the many states solve the problem. And one of them is the physical state, but generically you don't have a degeneracy, so there's one unique solution you get out. Thanks. There seems to be also this extra fluctuation at long distances. And if you look at the value of the R that this fluctuation, or the period of these fluctuations, they seem to almost match what you would expect from a Wigner crystal at that filling. And our current understanding is this is how things work, of course. So here you get a rigorous guarantee on that this is the lower bound on the energy. But the structure factor, the correlation function you get, is not necessarily physical. Actually, it's almost certainly not physical because this is the physical space, and we're searching a bigger space, and we're minimizing a linear functional on this convex set. So the minimum has to lie on the boundary. And the boundary is almost certainly, like, except in a few cases, the boundary is almost certainly outside the physical set. Now, if our results have converged, we expect that the correlation function we get should be close to the physical correlation function. But generally, in particular, if there are two closely competing states, we may expect that what this program would give us are what I would call a correlation function corresponding to some compromised states, which means they're correlation functions that has features from both the competing states. And we haven't yet imposed enough constraints to force the system to pick one of them. So this is kind of opposite of what would happen in a variational method. Usually in a variational method, if you have two closely competing states, the actual ground state could actually have correlations from both of them. But if your ansatz cannot account for both correlations, you're just forced to choose one or the other. Here, you're kind of doing the opposite. The correlation function you get could have features from two phases. Of course, the biggest feature we see is this r to the sixth that's associated with the Laughlin state, but these enhanced fluctuations here are, in a sense, an indication that there's some susceptibility, at least some susceptibility to nearby Wigner crystal. And of course, one would need them to systematically go up in constraints to see how these fluctuations get suppressed. I want to say something that there's an interesting quantity. I mean, the way we implemented things, we don't really have access to entanglement, which is something that can allow us to characterize the kind of the topological order without going through allow us to characterize the topological order without looking at very specific correlation functions and comparing to some specific model wave functions. But there's this other entanglement measure called the particle entanglement, which is based on basically just doing a particle cut rather than a spatial cut. So for a Fermion wave function, what we can do is we just split the wave function into p particles and n minus p particles, and then look at the standard way you do entanglement. And clearly, this is very closely related to the PRDM. It's basically just taking the eigenvalues of the PRDM, taking the minus log of them. And what you can show is that most of the well-studied model states for quantum systems like Laughlin, moir, and so on, these are the states that have something called the clustering property, which means they are zero modes of some specific p-body interactions called pseudopotential. Now, it's not very hard to see that this implies that these PRDMs will have a certain number of exact zero eigenvalues. So there are certain states in this projected space that the density matrix have to have zero weight on. In the entanglement spectrum, this would mean that there is a certain number of low energy states and there is an infinite gap to the rest of the states, which are obtained by taking the minus log of zero. And it was, at least in some of the kind of quantum Hall numerics that tries to diagnose phases from, for example, from ED, this kind of entanglement gaps and the counts of states below this entanglement gap in the particle spectrum has been used as a way to diagnose states that should be close or similar to, for example, Laughlin state or moir state. And if we consider this entanglement gap measure in our system, we get exactly the right count we expect for the Laughlin state. So and we have a very large gap between these low-lying states and the higher-lying states, which are kind of indication that our state is the density matrix describes something that's very close to the Laughlin state, at least as far as the as this particle entanglement aspect goes. The last thing I want to show is what happens if we do half filling. And the first thing that strikes us from when looking at what we get at half filling is that we see a very clear feature at 2kF. It's okay. I'm not showing a cut here, but it looks much more like a kink than a smooth peak. Although we need to do more careful kind of finite size scaling and also scaling in the number of constraints to tell this apart. But I show a little bit later that we may have that there's other indications that this is actually a CFL. Of course, you can just also look at this pair correlation function and compare it to some of the pair correlation functions computed for CFL and other systems. And you see that there is an overall good agreement, although there is this bit of mismatch with the period. And at the moment, I cannot tell if this is a real feature or because we haven't found very good systems on the torus. We haven't found ways to compare our results, which are on very large systems on the torus, to some kind of reference system under the same conditions. So I don't know whether these are kind of effects from the geometry or real. So they're related to finite size effects, or they are actually real to the method at the moment. And yeah, I think I wanna close soon, but I just wanted to show one thing, which is that there's a nice way to characterize what is physically going on in this method and what aspects of what is the main source of error in the approach, and why, for example, did we have this peak in the error as we doped the electron doped the Laughlin state. So a very convenient way to parameterize this SQ is in terms of Laguerre expansion. And then we get these coefficients, Cn, which are labeled by odd numbers, and they have to be positive, I mean, up to some shift. That's one thing. And the other thing is the interaction, the energy has a very simple form in terms of these variables and in terms of the pseudo-potential. So if we look at this C1, C3, the first two coefficients, this phase space in the first two coefficients, then for a short range interaction, the biggest term in the Hamiltonian is this V1, which means the short range interaction wants to push everything to this line. So if we're at 1/3 filling, we expect that there is a unique state that is a zero mode for V1, which means that this line should intersect the feasible region at a point. And this point should be the Laughlin state. Now, when we do this bootstrap with the different levels of constraints, we can actually map out the region. And we see that if we only use this 2-level constraints, we get this big region that starts shrinking as we include the 3-level constraints. But the region haven't completely shrunk, so we still have a finite line, which all are zero mode. Although there's only one physical state that's a zero mode for V1, the method still thinks that there is a finite range of possible values that are all zero modes of V1. Of course, because we are considering short range interaction, so to split this degeneracy, we just we add an infinitesimal V3, and this leads our algorithm to pick this point. And that point corresponds precisely to the correlation function I showed you, which have the same energetic properties as the Laughlin state at short distances, but has these extra fluctuations. And there's another interesting consequence of this picture, which is the following. Let's say now I increase the filling compared to 1/3. So again, what I expect is, because at 1/3, I had the Laughlin state was a unique zero mode for V1. And as I dope it, I should have no zero modes, which means I should have this region detaching away from the y-axis. But because the bootstrap is actually working in a bigger region than the physical region, when I add one electron, this region haven't detached yet from the y-axis, and it only happens after 2 electrons. So that's the origin of the high error when I add one electron. So in the actual answer, there should be a gap, immediate gap. But in the bootstrap doesn't realize there is a gap yet. But interestingly, it realizes there's a gap after I add a finite number of electrons. So if I look at the compressibility, I see a very funny structure where the incompressibility gaps that are supposed to be associated with the Laughlin fractions are actually shifted from the Laughlin fractions. But interestingly, the magnitude of the gaps is correct. Like this region. So the physical region, this ring around the physical region somehow doesn't depend on the filling, so it moves rigidly. And as we add more constraints, we'll see that this shift in the incompressibility peak moves towards the actual fraction. But I believe that you really need to include constraints of all orders to get this all the way to 1/3. So we have checked that this doesn't really change, like as we scale the system size, this is really a density shift, not a particle number shift. And as we add more constraints, it moves towards 1/3. So the more natural, I mean, it could of course be that it goes like this and then immediately hits the right point. But the more natural thing is that it asymptotes, asymptotes towards it as we add more and more constraint. So we do expect that we can only that getting the simple fact that the Laughlin state is incompressible would require kind of a sophisticated way to go higher to higher level constraints, not just keeping these few body constraints. And I think this is related to the fact that actually proving that Laughlin state is incompressible is a hard problem in mathematical physics. It's still an open problem till now. So yeah, so I mean, if we got this peak, we could basically solve this problem numerically. We could prove that the Laughlin state is incompressible, which is, yeah, it's 30-year-old problem. I will not discuss there's some recent results we have about interpolating between 0th Landau level and 1st Landau level, and we see what appears to be a kink that probably indicates a transition from a composite Fermi liquid to a different state. We have more evidence about that, but I will skip that and just get to the end. And I just, at the end, I would just want to discuss a few kind of an outlook for a future direction. So this was, in a sense, the way I view this kind of was a first attempt to use a kind of a very new approach to a well-established problem, whereas with maybe a promise to use this to answer a lot of questions that other methods cannot answer. And of course, you know, as a first step, we're doing there's a lot of exploration and experimentation here in what I showed you. But there's a lot of kind of interesting directions to pursue. One of them, as I said, that a lot of questions, although the method does get a lot of the basics that we know about the system right, there is some questions, like for example, the gap of some states that seem to require us to go to higher level constraints. And of course, the obvious ways to do this would not work because using either higher RDMs or just fixing even fixing just the structure factor, but trying to use higher constraints becomes very quickly unfeasible. And I believe that some questions actually require going to all orders in p-body constraints. However, there are new ideas that are very exciting where you just add a small number of these higher level variable, higher RDMs and higher constraints in a way that ensures you only keep the important information. So there is this renormalization group coarse graining approach that was introduced in this paper, and also there was some follow-ups work by people here in the audience, which basically attempt to expand the space of variables and constraints, but in such a way that to avoid the exponential growth, but at the same time keep the most important physical information. You could also try to develop certain heuristics based on kind of our understanding of the problem that give us good guesses of how to approximate the constraints. At the end, all of these constraint matrices are they are candidate matrix operators that we want to impose the condition that they're positive semi-definite. And if we think of these as Hamiltonians, and these Hamiltonians are actually, if we have a good guess of what the state should look like, then we have a good guess of what this Hamiltonian should look like. And if we have a good variational estimate, variational idea of the low-lying subspace of these Hamiltonians or these matrices, we can actually get an approximation of the constraints. And one interesting question is, actually, it seems that this allowed region evolves with filling in an interesting way. So in the figures I showed you, it seems to deform, to mostly shift, but deform very little along the shift, unless it hits kind of one of these walls that correspond to very specific constraints. And I was wondering if, I haven't seen a lot of any discussion of this question of how does this space of RDMs or space of correlators, which is a complex set, how does it evolve as a function of some variables? And yeah, the kind of questions you can ask is, of course, you can use this so you can think of this as a kind of generic method that you can apply for any one-body system, but there are particular things that this method gives you that other methods will not, which are rigorous lower bounds. So for example, you can lower bound excitations in gap states, for example, in the quantum hole, neutral modes or charge excitations. If we want to keep all the simplification from magnetic translation, there's a lot of possible generalizations for multi-flavor Landau levels. You can use it to try to drive lower bounds on superfluid stiffness, spin stiffness, Drude weight, which are all kind of interesting questions for many body models. And there is recently, there's also finite temperature extensions of this method. So I think I took way longer than I know was planned, but I hope it was useful, and let me end by just these concluding remarks. Thank you.
So this method respects particle hole symmetry.
Yes. So
Automatic.
it kind of happens automatic. So what happens is that these two-level constraints, like many of the constraints, they have a particle hole conjugated version. But if we impose all the right constraints, we see that if we do 1/3 versus 2/3, we get exactly the same correlation function. And yeah, and all the figures, if we do anything as a function of filling, it looks symmetric around. So we tried to impose it explicitly, but it turns out it's taken care of, so we didn't need it.
There are no more questions. Let's thank the speaker again.
So